Well, good morning, everybody. Welcome to the QFE seminar. We are very pleased to have you join us today. We're in for a treat because we have VRI Acharya, who is going to give us a peek at a new research project that he's doing, which is incredibly relevant to our times. He's trying to figure out what's the value of a cure for COVID and use what we see going on in the markets as a way to calibrate this. So we are very happy about this, and I think it will be an interesting talk. We have another QFE coming up in early December by Gernot Wagner, who is not only at NYU's Steinhardt School, but also is the Bloomberg columnist on who writes a column called Risky Climate. And it's very interesting read. He's a co-author with Bob Litterman and Kent Daniel on the one of the leading climate models of economic behavior. And so I think this will be a very interesting talk. He's going to be speaking on December 7th. So please stay tuned for that. So without any further ado, let me turn this over to you, Viral. We'll go for about an hour, and at 1:15 we'll take questions. Although if you want to ask a question, you can probably put it in the chat before that, and we'll see if there's a break where we can look at those things.
Great. Thank you, Rob. And do we continue for 15 minutes afterwards, sort of like a coffee session? Or?
Yes, exactly.
Okay. Okay.
So it goes till 1:30.
1:30. Perfect. Okay. Thank you, everyone, for joining. I see my co-authors, Tim Johnson and Suresh Sundaresan in the webinar. I also want to make a special mention of Stephen Zhang, who has been a research assistant and has been truly outstanding in helping us address this issue. And I also want to thank the Vaccine Center at the London School of Hygiene and Tropical Medicine for sharing the data that we are going to use for constructing our vaccine progress indicator. So let me start out with the kind of news that we have gotten used to seeing. I'm going to share a couple of positive news on the development of the vaccine. Both of them relate to this firm called Moderna, which is using one particular style of vaccine development. And on May 18th, it released positive interim clinical data from phase 1 trials, which tend to be on just about 45 individuals. And it also simultaneously announced dates for its phase 3 trial. And what's interesting, as observed by Matt Levine in his column Money Stuff in Bloomberg, is that the release of this news was like a common factor that moved the US stock market by about $1 trillion of market cap. Now, there may be other things that are happening that day, but what's interesting is that also the cross-section of the market impact seems to make sense. And also that the impact that we are seeing on the market as a whole seems much larger than what would be the value of the vaccine companies themselves. The second piece of news on July 15th relates to them actually publishing details of their positive phase 1 data in the New England Journal of Medicine. That the vaccine produced antibodies in all 45 of their patients. And you can imagine the kind of cross-sectional response that this would produce, since vaccine takes you out of the pandemic potentially once it's deployed and delivered in large quantities. COVID-sensitive sectors such as cruises, airlines, hospitality, industry, etc., seem to have massive reactions on that day. So, Matt Levine quotes in his July 16th article that, the cruises, the airlines were up anything from 15 to 20% over this period. And that vaccines are pretty important to thinking about economic outcomes, not just market outcomes, and thinking about the impact of the pandemic. Also finds some voice in Jay Powell's interview with the CPS, where he refers to the full US economic recovery taking at least until the end of next year, and as a necessary condition, it have the development of a COVID-19 vaccine, because he says that people will have to be fully confident in their choices, and this may have to await the arrival of a vaccine. So our paper is an attempt to put all this together, and as Rob mentioned, estimate the value of a cure that we might attach. Now, I want to be clear, there's a technical difference between a cure and a vaccine. A vaccine is supposedly for the susceptible who are not yet infected. The cure is for the infected, but we are thinking of it just broadly as a cure out of the pandemic. And maybe given that susceptibles are such a larger population than the infected, maybe it's okay to call a vaccine a cure. So what do? We are going to develop our own vaccine progress indicator using clinical clinical trials data on the individual vaccines and the news items that are arriving. We are then going to document the joint behavior of stock prices at market level as well as the cross section of industries. And then to make economic sense of this joint behavior, the fact that the market return has a significant co-movement with the vaccine progress indicator, we are going to build an asset pricing model in which pandemics and non-pandemics are regimes. The pandemic itself can have several substates to reflect the progress of these vaccines. So you get closer to exiting the pandemic as you go through these substages. It'll be a general equilibrium model. So the representative agent is going to choose labor and consumption endogenously to mitigate the economic impact of the health risk that arises in the pandemic regime. That will allow us to endogenously figure out the pricing kernel, price assets, and then ask the question, what is implied by the observed covariance of the market with the vaccine progress indicator? The vaccine progress indicator is going to be in terms of expected time to arrival of the vaccine. Both this expected time to arrival, so the expected time of exiting the pandemic, and the market returns will have their counterparts in our theoretical model. And together, they're going to imply that with the standard preference parameters used in asset pricing, the economy would value the vaccine at about 5 to 15% of its total wealth. In our case, that's the capital stock of the economy. Interestingly, this value of a cure in our model is intimately tied, as you can intuitively relate to, how much labor is withdrawn in the pandemic regime relative to the non-pandemic regime. And that's going to be a key driver of the value that you attach to the cure. And the sensitivity that we estimate of the stock returns to vaccine progress indicator are in fact going to map into about 25% of labor contraction in the pandemic state relative to the non-pandemic state. And I find that interesting because I just saw a recent Deutsche Bank piece circulated by their chief economist, which suggests that about 22% of the employment in the US economy is in highly contact sensitive industries. So if you took that as sort of like the total loss of jobs, it fits into that ballpark. Now, of course, the value of the cure increases in the pandemic intensity and its duration. And that highlights that these are crucial parameters to know in this sort of an economy. But of course, we don't know too much about them given how rare these events are. And so we, in the final stages of the paper, which I might not get to, we introduce uncertainty about the frequency and duration of pandemics that the agent learns from the arrival of a pandemic and exiting or not exiting the pandemic. So the agent's going to update priors on the frequency and duration of the pandemics. And what we find is that these have a hugely important role to play in calculating the value of a vaccine. In fact, the agent would be willing to pay as much to resolve uncertainty about these parameters as the agent would be willing to pay for the cure if there were no uncertainty about these parameters of the pandemic in the first place. We think it's an interesting result because it highlights that asset prices going forward, if these pandemics are going to be frequent or related disasters are going to be frequent, or at least it's something we are going to factor into asset prices, then we need to understand the biological and social underpinnings of the pandemics and their impacts. Formally, as I've already highlighted, we will have a regime switching model of pandemics. We're going to do it in the state of the art as far as preferences are concerned. So we're going to use the stochastic differential utility or Epstein-Zine preferences. And I want to stress that we are not taking the asset pricing kernel as given. There's going to be endogenous labor and consumption choices, which in general equilibrium will affect the asset prices. I want to stress one view on parameter uncertainty and learning, which is that a lot of scientists are beginning to consider that maybe this is not the big one, maybe more are coming. There is interesting articles relating climate change to pandemics, saying that maybe this is happening because of global warming and the movement of wildlife away from tropics towards the poles, bringing them in touch with diseases and germs they are not used to. And then the zoonotic diseases are coming and hitting the mankind. Those are the strengths besides the construction of the vaccine progress indicator of our model. Caveats are that we are going to adopt a rare disaster kind of model rather than an SIR style model. So our dynamics of the pandemic are not as rich as the SIR style models. So there's some trade-off there, as you'll see. We also don't have any policy such as fiscal or monetary support in our model. So when we take to data in understanding covariances, we have to control for these shocks from these events. Of course, these are things that are potentially worthwhile for further extensions of the model. Okay, in interest of time, maybe let me not get too much into the related literature other than mention that the vaccine papers are the first ones, the Harrison, Hong et al. Papers. They also use stock returns data, but what they do is they postulate an asset pricing kernel and an impact of the pandemic on the earnings process, as well as of the vaccine arrival switching you out of the pandemic. And then they try to calibrate it using the analyst earnings forecasts to back out the estimated arrival of a vaccine. Our approach is going to be slightly different. We are going to use actual progress of the clinical trials and the news to estimate a vaccine progress indicator. Then we are going to build a model in which pricing kernel is endogenous to agents' mitigation responses. And then we are going to establish what the covariances are. So there's an important departure, but clearly that work is related. Venki, who's in the audience, has a nice paper with Laura and a co-author where they have also learning in the model about the pandemics. It's more about the policies that will be in place next time around. And they show that there could be some long-term scarring effects. It's not the focus of our paper, but you can see that with learning, there would be impact on future consumption and labor as well. The effects may be mild year to year, but they can accumulate over a period of time. I also mentioned a couple of other papers that are related. Empirically, what is interesting is that there has been a very significant contraction of labor, and now that's documented in a variety of papers. The numbers range anything from 20 to 40% in terms of jobs that have been lost. And of course, there's this whole literature on working from home that's interesting to relate to. And we will show you something on the cross section of industries because those sectors will have greater labor contractions. And in a variant of the model where you had more sectors, that's what you would anticipate. And finally, on consumption, what's interesting is that while overall consumption has decreased in a discretionary sense, there was at the beginning of the pandemic a stockpiling that happened. You can think about it as agents using their buffer stock and converting that into consumption. We'll see that such effects can arise in our model as well. But as the pandemic progresses, you could also see a decline in consumption that arises. Okay. So the roadmap is that first I'll show you our vaccine progress indicator and the empirical results, then build the model of repeated pandemics and endogenous asset pricing kernel. Then we'll calibrate the model to match the observed empirical sensitivity of stock prices to the vaccine progress indicator. And then if there is any time, I'll talk about learning and parameter uncertainty. Okay, so our vaccine progress indicator should be thought of as constructing an estimate of expected time to vaccine deployment. We're going to construct this using the chronology of stage-by-stage progress of individual vaccine candidates and related news. And conceptually, what we are doing is very close to a first to default model in credit risk literature, where you may have a basket of several firms. They have their own likelihoods of default. They could even be changing ratings, and maybe therefore you have several stages until you reach a point of default. And in a first to default basket, the key point is which of these multiple names in a basket likely to break out into the default state the first. And very often this is done, these protections on first to default are valued using sort of simulation strategies to construct these first to default scenarios. And that's what we are going to do. So we have several candidates, about 231 of them. We have data on them that's updated weekly by London School of Hygiene and Tropical Medicine, from the World Health Organization, clinicaltrials.gov, Milken Institute, the vaccine developers themselves. And the data tells you information about the progress of the vaccines across these stages, from preclinical to small trials like Moderna's phase 1, phase 2 that then goes into hundreds, and then phase 3 gets into the efficacy stage of delivering several thousands of the doses and having the control versus treatment very fully possible because of the large numbers. And then they apply, get approved, and deploy. And what's important is that we have to map these stages into certain probabilities of moving to the next stage in order to be able to simulate this first to default style basket process. Of course, the number of vaccines, as you know, has been increasing. Right now, if you look at what's in phase 3, there's basically 6 of these candidates which are driving most of the data. But of course, it's important to do this for the full range of candidates, because as we will show you, and we have seen just in the past few weeks, negative news can also arrive on advanced stage candidates. In fact, there have been some side effects in phase 3 trials of Johnson & Johnson and the Oxford AstraZeneca vaccine candidate, which have put some halt on their progress. So what we do is using both past data on vaccine development for other kinds of epidemics and using some heuristics, as well as trying to match to some survey data that is out there on the expected time to vaccine deployment. We map each of the stages into a base probability of moving to the next stage. Okay, so the pi as base in that table tells you the probability of success to the next state. And then tau s is then the expected duration of that stage. So there's some, I would say, fair bit of judgment involved in these things. Of course, the choices we make here will affect the actual expected time to deployment. But since we will be interested in changes in the expected time to deployment and correlating those changes with the stock returns, what's more crucial is that you are tracking the progress correctly rather than getting the exact level of the series right. Now, many of these candidates have correlations between them, just like the names inside a basket of a first to default protection. What might the correlations in the defaults come from? They might come from a similar, of course, that you are after the same virus. They come from the fact that they share common institutes. So several firms have two different kinds of strategies at work at the same time, but maybe there might be some common factor related to their productivity or quality. And of course, trials of different companies on the same platform may also have correlations because, maybe a particular strategy has a likelihood of survival that's similar regardless of the institute that pursues it. So again, we make some heuristic assumptions on these correlations. We have a 0.2 as the baseline correlation in these base case probabilities. If it's a shared institute, we add another 0.2, and if there's a shared strategy, we add another 0.1. So roughly our simulation works as follows. On each day, whatever is the number of candidates at that point, we start drawing their simulation. So let's say we have 231 candidates, then we draw 231 multivariate normal random variables, and then we transform them into an exponentially driven time to next state and the failure for each candidate. Okay, so this is not the entire simulation being drawn from current state to exiting or not. It's only to the next state. Now, based on that, you know if candidates have a time to next state that's lower than time to failure to advance to the next state. In that case, that candidate goes to the next state, and then you repeat this process of drawing the normal random variables to move to determine the transitions to the next state. If the candidate has a time to failure that's lower than expected time to next state, then the candidate has failed, and that's it. And in a given simulation of candidates that get deployed, you calculate the minimum time to deployment, and then we repeat this for 50,000 runs to calculate the expected time to deployment at a given point of time. Okay. Now there's an important right arrow there, which is the news and decay. And I want to talk a little bit about how to do that. But roughly from our simulation, you can get data of this type, which is that as we moved from Jan 20 till end of August, which is what we have done so far, how did the expected time to deployment of the vaccine evolve? And because we have the simulations, we can calculate some statistics around this time to deployment as well. And one thing crucial to note is that that overall the vaccine progress has been very rapid during this pandemic compared to others. The time to deployment has shrunk very quickly from about 4 years, which is the base case, to about less than a year. Right now, it's around 0.6 or 0.7 year. Maybe the bad news that has come in the last 2 weeks could have set it back a little bit. But this is useful to keep in mind when one thinks about the overall stock market behavior as well. And this is a point that Hong et al. Make also, that the stock prices will be very sensitive to this arrival rate of the vaccine during a pandemic. Okay, so how do we factor in news and decay? Essentially, the way to think about news is that it's an augmentation to this base case probabilities that we have. Okay, so this requires a bit of textual work. We get the data on the news from FactSet, and then we have to map them into different kinds of news. Some of those will be positive types of news, some of them will be negative. Within each category, positive or negative, some are more important news than others. So some may revise the base probabilities more than others. So we have a mapping that takes the news in this set omega into negative and positive news, and then that affects the base case probabilities by a map delta pi. Okay, and so if you are standing at a given date, then there have been news about a candidate all the way from date zero until now, and you have to collect all these deltas in order to augment the likelihood of moving to the next stage. Now, no news is perhaps bad news in this sense. And so we have a decay rate for the days when there is no news about a candidate of positive progress. And then we can adjust the pies. We have to do it in a manner that helps us ensure that the probabilities are, between 0 and 1. So we have some transformation to do that. So positive news, I've already given you an example. As I mentioned, we have negative news. AstraZeneca, Oxford, and Johnson had pauses because of some, spinal cord infection that developed in some patients in their phase 3 trials. And we have, as of now, so those latest news are not in our sample, but we have 161 articles on news about vaccines, which we categorize into 13 news types. I'm only showing you a few of these here. And then we have this map into the delta. Basically, negative data or negative regulatory action revises very significantly negatively the base case probabilities in our simulations. And so ultimately, I have just reversed the figure that I showed you earlier. This is our vaccine progress indicator. We can do this daily, every night, by seeing what additional news has come. And it's inverted on the y-axis to give you the years to deployment of expected time to deployment of the vaccine. As of August 31, it was 0.6 years until deployment. Okay. And you can see that there was a lot of good news up until May, June. And then, of course, good news is coming only in smaller pieces until then. Next, I want to show you the stock market returns. So this is the black line, and it's on the y-axis on the right. And this is the cumulative return since January of 20. So you can see that first as the pandemic hits, which can be considered as switching from the non-pandemic into the pandemic regime, there's a massive collapse. At that point, the time to deployment of the vaccine is still pretty high, 3.5 to 4 years. And while no proof in itself, you can see that, of course, broadly, these two series have moved in line, and that this may be something to keep at the back of our minds when we think that perhaps there's some disconnect between the stock market and the real economy, because the stock market's value may be far more forward-looking, and the fact that the vaccine progression has happened in such a compressed period of time may be a very, very important piece of news for the market as a whole. Okay, I'll spare you some of the other events that have happened, but we can even individually zone in on specific news, etc. But maybe this is more important. There are two other sources where information about the vaccine is being gathered. The Deutsche Bank survey gathers actually a histogram of this type, which is they ask surveyors for when do they see the vaccine coming out, and they have various bins in the next 6 months, 6 to 12 months, etc. And so you get a distribution out of that. And we can relate our vaccine progress indicator, which we can do overnight, as I said, to the monthly snapshots that they have. And, we are sort of in the ballpark. In July, we are a bit further ahead of them. There's another survey called Super Forecasters, which is also providing this data every month on the median time to deployment of a vaccine. We were a bit lower than theirs until July, but in August, our vaccine progress indicator has gone a bit in the other direction. The vaccine progress indicator is now indicating about 0.7 to 8 at the date where they provide their 0.5 years of estimate. But it's sort of roughly in the line, indicating that some of the heuristic parameter assumptions we have made are giving something that's in line with these surveys that are out there. Okay, so what is the next step? We have to see how the stock market sensitivity is to this progress of the vaccine. So we are essentially going to run daily regressions of stock market returns on vaccine progress. Of course, this is a very daunting exercise. You have very limited data of 8 months from January to end of August. And we know there are many big days in this thing about policy interventions, etc. We also recognize that the vaccine news itself is sometimes not dated correctly, and sometimes it may even be leaking to the market before. We see some evidence of this about a day before. We also control for lags of market returns to allow for some illiquidity. And importantly, we take out the Baker-Bloom et al. Days of large market moves that can be specifically attributed on non-vaccine jump days to the kind of news item, macro news items that they track, which may involve policy support, fiscal, monetary, etc. So this is what it looks like. So we have the market return on the left being regressed on the change in the vaccine progress indicator from -1 to +2. Sorry, -2 to +2, and that should be a -2 in the indexing. It's 5 days. We control for 2 lags, and then we control for the Baker-Bloom et al. Jump days. And what we find is that the loading on the vaccine progress indicator ranges from -4 to -6.3. It's statistically significant only in columns 2 and 4 at about 5.8 to 6.3. And basically there is some differences in these columns based on whether we are using news to update all states going forward, or whether the news are only updating information about the progress in the current state. So there seems to be some dependence on that in our empirical results. So statistically, it's kind of borderline. As I said, it's only significant at 10% in 2 of the columns. Of course, we have good economic reason to believe there should be such a sensitivity. So we welcome ideas on what else we might be able to do to identify this better. But we'll see that these magnitude of 4 to 6. So let me just explain how to interpret this. The way to interpret this is that if the expected time to deployment of the vaccine decreases by 1 year, the stock market has a jump of 4 to 6.3% on a daily basis. Okay, that's the way to interpret this coefficient. We think it's quite large. What gives us confidence in the vaccine progress indicator is the second body of results, which relates the cross-section of industrial returns, the Fama-French 49 industry returns to the vaccine progress indicator. And we see that on the right, you have sort of almost COVID positive sectors, such as medical equipment, for example, or pharmaceutical. Or the defensive sectors such as precious metals. Those are very, very stable: apparel, retail, etc. They have very low sensitivity to the vaccine progress indicator. But as you go to the left, you have sectors such as banks, services, aircraft, construction, which have a sensitivity of even higher than -5, and sometimes as high as -10. In case of coal, it's very large. Of course, some of this may be noise, but there's a very clear cross-sectional pattern that the COVID-sensitive sectors are on the left and the defensive sectors are on the right. We see this sensitivity especially at t equal to -1 and t equal to +1. So the day after the vaccine news is released, which is this one, and t-1, which is that perhaps some information is getting leaked into the market the day before. So that's it on the vaccine progress indicator and the stock market sensitivity. We're going to take these numbers of 3 to 6 and now try to make sense of that in terms of what does that mean about the deeper parameters of the economy and the value that the economy would be willing to attach to a cure. Okay, so to this end, we build a model, a general equilibrium asset pricing model, which has repeated pandemics And it has the possibility of this notion of stages of a pandemic as the vaccines are moving across the different phases. So think about the state space as being non-pandemic state being 0. Then you could switch into the pandemic to state 1. Then you move across these gradual exit stages as vaccines are progressing. The last stage being S-1, and then you exit into state S, which is the same as state 0, the non-pandemic state. And this can just go on. Okay. So if you are in the non-pandemic state, which is 0 or S, you have a probability eta dt of switching into the pandemic. And then once you are in the pandemic in a given state S, you switch back and forth possibly between the adjacent states with probability lambda d and lambda u. So lambda d is a down move towards the non-pandemic, towards the pandemic states. Lambda u is an up move towards getting out of the pandemic. And then ultimately you may exit altogether. We are not going to have explicitly something that looks like a vaccine technology in the model, but you should think about these states as moving to relatively better states as you are going up from 1 to S-1. So what is the economy? There's a representative agent who owns a capital stock. This capital stock can be thought of as a buffer stock that's costless to adjust to convert into consumption. So the agent will make a consumption choice capital C in a period dt, and that's going to write down the capital stock by that amount. In each period, the agent also exercises some effort L, which will be over some range 0 to L upper bar. L upper bar can be thought of as like the normal time supply of labor. And that augments the capital stock of the agent, and that generates some drift mu. It grows, the capital stock has some productivity, but it also has some risk associated with it that's captured through the Brownian motion shock dBT. Okay, so you can see here that without the risk of a pandemic hitting you in any way, the optimal thing for the agent is to supply the highest labor L upper bar, because that just augments your capital stock. Okay. But there is going to be a pandemic that's going to produce a mitigation response by withdrawal of labor. So what does the pandemic do? We are going to model the pandemic as that as long as you are in this pandemic regime, which is the states 1 to S-1, there's a Poisson process PT that could trigger and cause a loss of the agent's capital from Q to Q times 1 minus chi delta. Okay, so capital delta is the jump amplitude of this process in its impact on Q. But the impact gets magnified by the labor supply. Okay, so there is some initial conditions which may affect your exposure. There's a small k. Your supply of labor L increases the exposure to the pandemic through this parameter epsilon. And there is a possible externality, which is that the aggregate labor supply, capital L, this is a representative agent economy. So capital L will simply be the small l, but of course the decisions are being taken by atomistic agents. But this capital L can also affect everyone's exposure to the pandemic through the exposure parameter capital K. Okay, so the total exposure is this Greek letter chi, which is a function of each agent's exposure and the aggregate exposure, and that amplifies the loss of capital that you're going to face if the pandemic hits you. Okay, so that Poisson process gets triggered. And the Poisson process has some intensity zeta, which is going to control the duration, which is going to control the intensity of the arrival rate of the pandemic. Okay, now how does the agent make the choices? So the agent has this stochastic differential utility, abstinence preferences. So it's recursive representation. The parameter psi is the elasticity of intertemporal substitution. Gamma is the risk aversion relative risk aversion coefficient for the agent, and rho is the discount rate. And so agent is going to choose capital C and the labor L to maximize J at each point of time. So basically we have to set up a rational expectations equilibrium here, which is that each atomistic agent is going to take the aggregate labor supply L star as given. Then given that aggregate labor supply assumption, they will choose their own consumption and labor supply, capital C of S and small l of S in each state that maximizes their objective. Then, given all this, you get the wealth dynamics in the pandemic regime because, you are augmenting labor, you are consuming out of it, and Brownian and the pandemic Poisson shock can hit you, and you control the intensity or the exposure to that. In a rational expectations equilibrium, the L star of S assumed by each atomistic agent will be the same as the choice that they made themselves. Okay, so then we can solve all of this. We can write down under the rational expectation what the HJB equations would be, the first order condition with respect to labor. As a standard in this setup, we have to conjecture that the value function is basically proportional to the capital stock raised to 1 minus the risk aversion coefficient. And in each state, the conjecture is that it's some fraction, some multiplier capital H of S on Q to the power 1 minus gamma. And solving the system pins down to solving these coefficients capital H of S that respect the first order condition with respect to labor, the HJB equations with respect to C, and the rational expectations condition that L star and L are the same in equilibrium. So, you can solve this, and it turns out that this system has a nice structure, even though it's a bit complicated. You can't solve it fully analytically. For a two-state case, you almost get a semi-analytical representation, which you can at least play around with and derive some properties. For the S-state case, you get a recursive system, as is typical in the regime switching stationary models. Essentially, you get that the model is characterized by this one function G, which depends upon the labor supply of the agent and the intensity of the Poisson process of the pandemic. So in the non-pandemic region, you have G0, which is on the middle equation, which is that in the non-pandemic state, the agent supplies the full labor, and there is no likelihood that a health risk will come and destroy your capital stock. In the pandemic states, there is a function G1, which depends upon the labor supply, which will be a mitigation. So it will be lower because you want to reduce your exposure to the pandemic so you don't get hit by the capital loss. And there is the zeta arrival rate of this Poisson process. And it turns out that this recursive equation that pins down the agent's objective function in these states, H0, H1, H2 until Hs minus 1, depends very crucially on these two quantities, G1 and G0. In particular, if you take the pandemic parameter zeta as given, it depends crucially on the contraction of labor in the pandemic state relative to the non-pandemic states. Okay, and then you need that capital S and 0 are the same states to then close this system of equations. So you can solve for the optimal labor. There is a mitigation in that, that depends upon the epsilon, which is the direct exposure to the pandemic. It depends upon zeta, which is how likely the pandemic shocks are. And it depends upon capital delta, which is the capital stock loss that occurs when the pandemic hits. Okay, so what does it look like? So let's take a case of elasticity of intertemporal substitution, let's say around 1.5, which is like an assumption that Bansal and Yaron make in their long-run risk literature. Then you are at the bottom of this graph. On the y-axis, I'm showing here the marginal propensity to consume in each state. And on the x-axis, you have the states varying from 0, which is the non-pandemic state, to 10, which is again the non-pandemic state. And in between, you have the pandemic states 1 to 9, and the pandemic states are getting better in terms of exiting from the pandemic as you go from 1 to 9. And with an EIS of 1.5, you actually get an increase in the marginal propensity to consume, a little bit like the evidence I was mentioning, that you actually first run out your capital stock to increase consumption, you consume out of your buffer stock. Then that comes down all the way to the original level once you exit the pandemic. Okay, so you can figure out the consumption in this model as well. And once we have labor, consumption, or the marginal propensity to consume, and the capital H's, which determine the objective function, we basically have solved the model fully when you do this. So what's the value of a cure in this setup? One way of doing it as a comparative static exercise is to calculate the certainty equivalent change in the representative agent's lifetime value function upon a transition from state S to 0 all of a sudden. Okay, so if someone basically just switched you out with a vaccine from state S to state 0 or state capital S, what would be the change in the certainty equivalent of the representative agent's objective function? And so, that's that quantity capital V of S over there. And you can transform. So you can see here that it's basically just the ratio of capital H's augmented by the EIS that maps 1-for-1 into the consumption levels or the marginal propensity to consume in these states. And this is the percentage of your stock that you would be willing to give up to be fully compensated, that you would surrender in order to get the vaccine and switch out. And as you can imagine, this is now going to depend crucially on the labor contraction between these states. And that is what I want to make precise next. Okay, so now we are on to this. We have finished 2 steps so far. We have shown you the empirical calibration of stock return sensitivity to the VPI. I have laid out the general equilibrium framework. Now, in this framework, we have an expected time to arrival of a vaccine because we have these stages and we have probabilities attached to this. But we have to calculate asset prices. So we are going to model the market as basically being a claim to the output of this economy. So the output of the economy is what you get in terms of change in the capital stock plus the consumption. And we'll denote the price of that as capital P. I won't bore you with the details, but it's non-trivial, but we can actually determine the pricing kernel under the stochastic differential utility with this endogenous labor and consumption choices, which factor in the pandemic risk. And it turns out to be a system of S+1 linked partial differential equations. Once again, we conjecture that the price of the claim in state S is some P of S constant times the capital stock at that point. And then we have to pin down these P of S's, which basically are equivalent to more or less quantifying your pricing kernel. Okay, so that satisfies these matrix equation. We can again solve for it numerically and do all the asset pricing work with that. And as I mentioned, we can calculate the expected time to vaccine in the setup as well, because we have these assumptions of transition matrix across these states. So why am I doing all this? Because just if you focus on the last bullet point, the quantity we estimated in the data was change in the prices divided by change in the expected time of exiting the pandemic. And now we can map that 1-for-1 into our asset pricing model. So we are using the structure of the model to learn about the deeper parameters which we don't have a value for by mapping it into the empirically observed value for this quantity, which was the sensitivity of market return to expected time to deployment. Okay, so this calibration on the face of it looks fairly non-trivial, okay, because the parameter space is very large. Okay, we have preference parameters, the risk aversion, discount rate, and EIS. We have the normal time capital stock parameters, mu and sigma. We have the pandemic parameters, which is, how much the labor augments the capital stock, zeta, the arrival rate of the pandemic, the exposure parameters to the pandemics, the background exposure, labor exposure, and the externality, and then how much the capital stock gets destroyed. And then we have all these switching parameters, how many states, what probabilities, etc. Now, while on the face of it, it's very complex, what's nice about the system of equations for the capital H's that I solved you is that it depends very crucially on those functions G1 and G0. Now, G0 is a property of the non-pandemic state, so it's not going to change with the pandemic parameters. G1 is going to change with the pandemic parameters. So what we can do is we can vary the sufficient statistic G1 and pin down the sensitivity of the market return to expected time to arrival in the model. Okay, that is going to give us a function of this type. So this is the model calibrated sensitivity of market return to expected time to vaccine as a function of G1, this quantity that depends crucially on the labor contraction, as we vary different parameters of the pandemic. Okay, so we are not altering the non-pandemic parameters, we are altering the pandemic parameters. And you basically get a function of this type. Okay, now what does this mean? What this means is that suppose the empirical counterpart is a sensitivity of 4%, then I can go on the y-axis, look up 4%. That gives me a G1 of about minus 0.35. And that G1 of minus 0.35 under standard preference parameters is going to help me calibrate the labor contraction that's going to be implied by this model. So what the model says is that the stock price sensitivity to the expected time to deployment of a vaccine tells you something deep about the labor contraction in a pandemic relative to the non-pandemic states. And we can infer that because we have the advantage of having the structure of the model that we can calibrate and then map into the specific value. So you get 0.4 to 6 was the range of the empirical estimate. So that's the band on the y-axis we need to focus on. That implies a G1 in the range of 0.35 to 0.42. And that then maps into the extent of labor contraction in the pandemic state relative to the non-pandemic state. So then we can put all this together and figure out the capital H's which are implied by that, calculate, plug it into this formula for the value of a vaccine, and all of that then gives you a value of the vaccine. So what do we observe? That if we just assume pandemic is a one state, so you have non-pandemic and pandemic state, and then just a vaccine arrives and takes you out, just for sake of illustration. You have eta equal to 0.02, so a pandemic happens once in 50 years. And let's say that the likelihood of switching out of a pandemic is in 2 years. In that case, we get that the agents would be willing to give up about 5% of their wealth for an immediate transition out of the pandemic state. And this corresponds to how do we get the 5%? Because the G1 that we observed implies a labor loss of about 25% in the pandemic state relative to the non-pandemic state. Now, if I lower this lambda u, um, so the likelihood of the vaccine is lower. So lambda u is 0.25, suppose. Then the expected duration of the pandemic is 4 years, and the value that the representative agent attaches to the vaccine would increase to 15%. And as you can imagine, what's interesting is that if pandemics are more frequent, so as eta increases, so now that's on the right-hand side scale, the pandemic frequency, as eta increases, the pandemics are going to be more frequent. And then you don't value a one-time cure as much because you are just getting it to get out of the current pandemic, but another one could be following very quickly. And so your utility doesn't improve as much from just taking care of this particular pandemic that you have. So this is our main sort of calibration result, that the observed stock market sensitivity to the vaccine progress indicator of 3% to 6% implies about a 25% contraction of labor in the pandemic states relative to the non-pandemic states. And depending on what you assume to be the pandemic frequency and pandemic duration, which is arriving, say, about once in 50 years and having a 2 to 4 year duration, you get that the value that the economy would attach to a cure would be on the order of 5 to 15% of its capital stock. Okay, a couple of interesting things. I'll just quickly summarize these results. One value of the model is that we can solve here for the planner's problem, because planner would internalize the fact that capital K is an exposure that every agent creates for other agents in the economy through their supply of labor. And so the planner would actually adopt a mitigation strategy or withdrawal of labor that's greater than what each atomistic agent would. And because the planner doesn't expose the economy to capital stock distribution from the pandemic as much, planner would actually care less for the arrival of a vaccine than a strategy which doesn't contract labor as much would. Now, I've always believed that one should not confuse between central planners of our model and the governments we have. It's possible that in many countries, governments are actually the benchmark model, which ignore the externalities. And maybe the central planner is a theoretical construct in the mind of the epidemiologists or the scientists advising the governments who have been ignored in many countries. But the interesting point here is that if the mitigation strategy doesn't factor in the externalities and therefore is less severe than the optimal strategy, then that strategy would value the vaccine a lot, because you are exposing yourself to serious economic losses from the pandemic by not withdrawing labor as much. And therefore, you really value the arrival of the vaccine a lot. In contrast, if you endogenize the externality and realize that you have to actually reduce the exposure to the health curve, then you would not actually value the vaccine as much. Okay. So we get that planner would value the vaccine about 1.5 to 2% less than what the benchmark decentralized case would. Okay, I have about 5 minutes max. So what we do in the last part of the paper, I think theoretically this is the most challenging part, where we introduce parameter uncertainty and learning. And we think this is very natural in the situation of rare disasters such as pandemics. So to keep it simple, we just focus on two states now, the non-pandemic state and the pandemic state, and then a vaccine arrives and takes you out of the pandemic. So eta is the probability that you switch into a pandemic, and lambda is the probability that you switch out of the pandemic. Now, there is no lambda u lambda t anymore. Okay. And we assume that eta and lambda are not known with certainty to the agents. They have common beliefs, and they satisfy these gamma distribution on eta, on their means and the variance of the distribution. Then it turns out that based on the cumulative time that you spend in a non-pandemic state, and the number of switches you have made in the past from non-pandemic to the pandemic states, you can update your priors of these two important pandemic parameters, eta, which is the frequency of the pandemic, and lambda, which is the frequency of switching out of the pandemic, implicitly the expected duration of the pandemic. The posteriors follow the same gamma distribution. It is just that the means and the variances get updated, which is that the more switches you have observed out of the non-pandemic to pandemic, the more you are going to augment the frequency of the pandemics arriving. And the more time you have spent in the non-pandemic states, correspondingly, you are going to update the variance of these estimates. And then we can do the solving of the model. As you can imagine, now there aren't just fixed number of states because each pandemic or non-pandemic is now conditional on the number of switches, etc., that you have observed in the past. Okay, so you have an infinite dimensional system indexed by M, where capital M basically captures this information about the number of experienced pandemics and the point estimates of these switching intensities. But otherwise, it still respects this G0, G1 structure that I had mentioned earlier, which depends on the contraction of labor in the pandemic versus non-pandemic. You just have a much more complex system of H's to solve now. Okay, so now the kind of exercises we can do are, how much does the parameter uncertainty matter? Okay, so what we can do is we can have a low uncertainty case in which basically you are just at the mean parameters and there is no uncertainty about the parameters. That's the top row. And we can have a high uncertainty case where we basically allow for a standard deviation in the parameter which is as high as the point estimate itself, both on eta, the frequency of switching into the pandemic, and lambda, which is the frequency of switching out of the pandemic. Now, it turns out that the impact of the uncertainty is to, in general, raise the value of a cure. Okay, so the more uncertain you are, the higher is the value of the cure. So that's a comparison between the top and the bottom panels. You can see that the value of a cure increases sometimes by as much as 3 to 6 times in these estimates. However, it depends the magnitude of how much you value the resolution of uncertainty depends a lot on the elasticity of intertemporal substitution. And why is this? When agent's elasticity of intertemporal substitution is high, which is in the right column, if you have uncertainty, some very bad states are going to arise because, with some probability, the pandemics are even more likely than in the base case estimates of eta that you have. If you have high elasticity of intertemporal substitution, you can deal with that by simply moving your consumption into the present states. Okay, but if you have low elasticity of intertemporal substitution, you can't do that, and you will want to move consumption into those disaster states, and that's going to be very costly in the anticipation. And so uncertainty is going to reduce your labor and consumption significantly, and it's going to raise your value that you attach to a cure. So at low elasticity of intertemporal substitution, the value of a cure rises a lot with parameter uncertainty, and you may be willing to pay as much for resolving that uncertainty as for the cure itself. So let me conclude. What have we done here? In some sense, there's quite a lot in the package, but I think there's a logic to it, which is the following, which is that our first contribution is this empirical construction of a vaccine progress indicator. To the best of our knowledge, this is completely novel. This has not been done to use the actual clinical data on the trials and map that into an expected time to vaccine arrival. Second, we then show empirical sensitivity of stock market returns to this, and we find that the daily market return has a sensitivity of between 3 to 6.3% for a reduction in the expected time to arrival of a vaccine by 1 year. Then we build a general equilibrium model with endogenous labor and consumption choices, and with repeated pandemics, and with this possibility of sub-stages of a pandemic that map into progress in the arrival of a vaccine. We can provide asset pricing kernel in this setup, which is micro-founded, and using standard preference parameters, we conclude that the stock market sensitivity to the vaccine arrival implies 30% contraction of labor, and that would mean that the agents would be willing to give up 5 to 15% of their wealth to give up to get a vaccine. In fact, when I asked Jeff Wergler, his estimate was 10%. He said he'll be happy to give 10% of his wealth to get the vaccine right now. So we thought that was interesting. Let me stop there. I'm happy to remain in the Zoom, take some questions, and have our virtual coffee break, so to speak.
Well, thank you so much for all. That's what a fascinating presentation, and covering just all sorts of things that everybody's interested in today. I mean, I have about 20 questions I want to ask. Let me just ask one or two, and then we can turn it over to the general audience. Which ones do I ask first? The effort to explain the stock market collapse and then recovery and so forth by information about clinical trials. I mean, is very interesting, but the alternative is that there is all this work showing that things like sustainable portfolios are outperforming, that fossil fuel based portfolios have lost money, and some of those are really different or fundamentally different, and others are merely sort of a part of what you're talking about. So I guess I wonder, aren't there some more variables that you need in those regressions that can really try to separate this out? And do the regressions, I can't remember when your starting date was, do they explain the stock market drop in March as well as the recovery, or are these just, did you start right after the recovery?
Yeah, so the stock market drop would be soaked up by the Bloom Baker et al. Dummy actually,
I see.
because that's just the switch into the pandemic, and there's not much happening on the vaccine at that stage. Most of the good news on vaccine is after
Well,
the
that was
pandemic has hit.
written,
Absolutely. But I think the stock market drop is very interesting because the model says that is exactly what you would expect once the switch into the pandemic happens. Because now you are exposed to this disaster risk that was not on your horizon at all. And because you have this disaster risk on the horizon, suddenly mitigation through labor contraction is going to come into play. And that's going to affect the valuations in a very, very significant way. Because the only way to mitigate is to not maintain the value of your capital stock. And the more you have to mitigate from a particular kind of capital stock, the bigger would be the collapse in its value. And I think with diversity of capital stock technologies, I think one could make sense of the coal versus the ESG kind of factors. Now, I don't think the coal versus ESG are directly affecting your exposure to this pandemic per se. But I think if you took a broader view that the pandemic has in some sense created now a regime in which you may be exposed to these kinds of risks in future as well, then it suggests that these kind of technologies would be valued more because of the scarring effect of the pandemic, which is that the pandemic has made you learn about the increase in the frequency and perhaps in the duration of these kinds of episodes. And maybe that has increased the valuation of technologies that don't generate such exposure in future relative to changes that you would. So I think the linkage, at least in our model, would have to be that coal versus ESG is a climate risk factor. The climate risk factor has some bearing on the zoonotic diseases, and through that, it affects actually the arrival rate of the pandemics, I think. But, of course, none of this is part of the model.
So then my second question, which is, it seems, I mean, you're seeing a lot of this happen through what I understand to be voluntary labor supply restrictions. People are not supplying as much labor because of the pandemic. I would think you could take that as exogenous in the sense that labor supply being a function of the state drives down labor supply, kills off some capital, reduces consumption. And I think of the reduced consumption as being really the driving force behind a lot of the sustainability results too. So, but I'm not sure that actually is a different model from what you have.
Yes, I think in principle, so I think what is key to the model is exactly as you said, that the labor supply contracts, whether consumption contracts or not, depends in these models actually on the elasticity of intertemporal substitution. But if you had low EIS, you would get a very big collapse of consumption as well. And then that would map into a revaluation of all the asset prices. Uh, I think in a way, what we are saying is that, and perhaps Tim or Suresh can correct me if I'm not speaking about this right, is that actually these responses would endogenously alter asset prices themselves. So it's not just a matter of figuring out the new consumption and plugging it into our standard asset pricing kernel. Um, in the model, actually, the asset pricing kernel changes fundamentally itself because of these pandemic risk in itself. Tim, Suresh, do you want to add to this in any way? I don't know if they can speak, probably not. Okay, they are in webinar format, so I guess they can't speak. Yeah.
Okay,
Yeah, but that could be another way to go. I think that's the one way to make sense of our G1 and G0 equations that I was showing, that as long as you give me the values of G1 and G0, I basically have figured out the objective function of the representative agent. Now, in our model, the specific structure of G1 and G0 comes from an optimizing agents problem. And therefore, there is a very specific set of combination of various parameters of the economy that goes into that G1 and G0. But G1 divided by G0 is like a sufficient statistic in this model for solving the model. And now there could be different ways in which this G1 divided by G0 can be constructed. You could just come up with it out of the blue, or you could get a little more structural and write down like an optimization model to do that. I think one advantage, Rob, though, is that because we want the sensitivity of the asset prices to the expected time to arrival of the vaccine in the model, what happens is that our standard asset pricing kernels don't necessarily build in the structure of the expected time to arrival of the vaccine. So the setup that we have has as its backbone in the state space arrival of a pandemic and then vaccine progression out of the pandemic. And then asset prices and the expected time to arrival are built on exactly that same structure. If you adopted a standard existing framework, you would have to still throw in the probability of the arrival of a vaccine and the arrival of a pandemic into it. And that's closer to what Harrison Hong et al. Do.
But if you took labor supply as being an exogenous function of the pandemic, you would get these asset pricing implications, I think, in the same sort of way.
Exactly. So we could just take an L star into the equation, and that would be all fine. Actually,
Yeah,
absolutely. Yeah.
An anonymous question is that we have heard that a possible vaccine might be only 60 or 70% effective. What is assumed within the model or implied by the model about the efficacy of any vaccine that arrives? Likewise, the rollout of doses and willingness of people to be vaccinated is uncertain. What's the model assume about the lag from announcing a vaccine until the rollout and the vaccination of the relevant population?
So we do have some uncertainty in the last stage of the vaccine itself, which is the deployment stage. Even there, the pi base is actually 0.95. It's only 95%. And so while we don't exactly model the lack of full efficacy of the vaccine, you could think about uncertainty even in the deployment stage as partly reflecting that possibility. That even even once you are at the stage of deployment, you get out of the pandemic only with a 95% likelihood. So to that extent, we have it built in. There could be other ways of doing it, and that could be also an interesting thing to do. One thing we haven't done, but which is entirely doable, this goes back to the earlier question that Rob asked, is that we could, in principle, construct long short portfolios that correlate with changes in the vaccine progress indicator. And that could be thought of as like a market trading portfolio that captures the cross-sectional evidence that I showed you, gives a sense of what it's going to look like.
Yeah. And Dick was, I think, going to ask exactly that question. And I did think that your cross-sectional evidence gives you the tools to do that.
Yes, exactly.
And then I guess you have to decide, since it's not a long-only portfolio, what's the value of the cure? It's some winners and some losers.
Yes.
And you have to net that out.
Yes. Mm-hmm.
Did you have anything more to say on that, Dick, that you want to?
Well, I was going to say, even with a cure, the cure, reflecting what you just said, Rob, the cure won't affect all businesses equally. And so cure in quotes may be nonetheless have a significant, the pandemic and its lingering impact may have a significant effect on business models and therefore on the winners and losers. And Matt Richardson also made the point about looking at it on a cross-border basis, which
I think we could definitely do that. I think that's one value of the vaccine progress indicator in itself, which is that it's kind of a little bit more direct about the vaccine evolution.
Yeah.
Whereas if we constructed some long short portfolios, it's possible that some market segmentation effects might possibly play out.
Absolutely.
Across different countries. But
yeah.
But I think it would still be quite interesting to do, I think, to construct this long short portfolio. What we don't have in the model is diversity of sectors. So, because then it would require further aggregation into the representative agent and so on. But in principle, you can see that at least if you did comparative static exercises, so if you varied the parameters which control your exposure to the pandemic, the epsilon. So when you supply labor, how much exposed you become to the pandemic, that's like a work from home kind of exposure index. And then you had this small k, which is your background exposure to the pandemic, regardless of anything, how exposed you are to the pandemic, regardless of whether you supply or not. And that could be thought of as perhaps, whether, I don't know if that's like a coal versus ESG kind of separation. Yeah, I think that's interesting. We hadn't thought about international stock returns, Matt, but I think we could definitely check some of these sensitivities for other global markets. By the way, I did have a fifth column, which was the global MSCI in that table. And that had a slightly lower sensitivity. That was around the estimate of between 3 and 4. Whereas the US sensitivity was a lot greater at, I think, in the 5 to 6 range.
That may reflect our cultural aversion to wearing masks in this country.
Yeah, actually, I think that's possibly true, because the model actually says that if you are not adopting enough mitigation, you would value the vaccine more, and then the stock market would be more sensitive to the vaccine progress indicator.
Many other questions to ask for all, but we were kind of running out of time here, right?
I'm afraid we are.
Great. Thank you so much, Rob, for the opportunity. And, we can discuss further about suitability of this for the... I didn't show the formulas for the copula and all that, but, I'm sure you can vet those and see whether there are things to do there or not. But yeah.
Yes. I mean, I think we should have a talk about the copulus and that first step. There's a lot going on in that first step.
Yes, yes. Yeah. Because I think
as a
Yeah.
as a final word, do you have any idea what, for example, the governments of the world are investing in a vaccine?
There is data on that, and in a way that is important because in our model there is no vaccine in the economy, but in reality, there are these technologies and people are making decisions on how much to invest in them, etc. And I think the government investments are sort of like an interesting beast because on the one hand, they may be accelerating the vaccine development if there is a financial constraint on part of the vaccine companies. On the other hand, though, very often the government funding is coming with caps on user fees for provision of the vaccines, which means that the stock prices of the vaccine companies themselves may not be that good a reflection of the value to the economy of the vaccine. And so one of the reasons I didn't make this point, but one reason why we haven't focused on value of the vaccine companies is precisely because of the involvement of the governments in this whole thing. Because then we know for good reasons, they may not capture all the value of the economy to the vaccine. But then, that's not good enough then to know what is the economy's worth for the value of a cure.
Vaccines are both
But we
a
do
public
have
good.
data on that. Yeah.
Yeah, they're
Exactly.
both a public good and a private good at the same time.
Exactly.
Terrific. Well, thank you very much. And
thanks, Rob. Yeah, we can set up some time to discuss
Good stuff.
the front end. Yeah, but the front end is written in the paper that Matt circulated. So if you want, at least it will give you a fuller description of the.
oh, I see. Okay, good.
Yeah, it's all written up in the PDF of the paper. So
Great.
Yeah.
Well, thank you very much.
Thank you.
And see you all later.